All right, so we're going to talk about polyatomic ions. So these polyatomic ions are actually molecules, just with charges. As you can see here, like you have chlorine and oxygen, which are both nonmetals. All right, so how do we figure out the number of valence electrons? With polyatomic ions, this is a little different. So this has 7 oxygen, we'll have 12, right? 2 times 6. This -1 charge means that there's an actual extra electron. So we're actually going to add an extra 1 here. So in total, it would be 20 electrons, okay? So the negative charge tells you, oh, there's an extra electron, right? A positive charge would mean, oh, there's 1 less electron, so you'd be subtracting that charge from it. And then we're just going to go ahead and draw the structure. So I used up 4 there. So that got me 16. I used up 12, and then that gives me 4. So, and then since this is an ion, we have to show that it has a charge, so we put brackets in the -1. So this would be the structure for Cl2 -1. This is actually not the most likely structure. This is not the most stable structure. And let me show you. There's something called formal charge, and you can write it down. But it helps to determine what the most stable structure is. And so I'm going to go ahead and show you this. So if you want to write it down, pause the video and write it down, you can. But I'm going to show you how it works here. So if we recall that structure, it looked like this. So I'm going to figure out the formal charge. So the formal charge is the number of valence electrons. And we're actually going to figure it out for each atom. So you want to figure out the formal charge for each atom. So oxygen has 6 valence electrons. And then you subtract that by the number of lone electrons. So there's 6 lone electrons on this oxygen, minus the number of bonds, so -1. So this would be a -1 formal charge on oxygen. The same calculation would apply for the other oxygen, right? It's the same thing, just the other side. And this chlorine is in a halogen. It starts with 7 valence electrons. There's 4, and then -2, there's 2 bonds. So it would be a +1. Now, with formal charges, so if you add these up, it equals -1, which is what it should. It should equal the overall charge. But in general, we like it when the central atom is around 0. There are exceptions, but it's better to have it closer to 0 if we can. Well, how can we get this closer to 0? Well, what we could do is, if we want to make this closer to 0, we could take one of these and put it here, like so. This would still work. Chlorine is a little strange now, but because chlorine has 10 valence electrons. But remember, chlorine is in period 3, is it? Or maybe past period 3. Chlorine's in period 3, and so it can handle having an extra outside an octet. So let's just take a look at this real quick. So we now have something that looks like this. But let's do the charges. Let's look at the formal charges real quick. So this oxygen now, it starts with 6, -4, -2, so it's at a 0. This oxygen, remember, we had a -1. But this chlorine now chlorine has 7 valence electrons, but it has 4, and then it has 3 bonds around it, so it's at a 0. This would actually be preferable. This would actually be preferable because its central atom is 0. And that's kind of what we want. All right, so that's kind of the goal. All right, so that is how you use formal charge. Now there's something else we got to talk about here, and that's called resonance. So a resonance is a way to show that there might be more than one possible structure. In reality, the structure is somewhere in between. And so let me explain this. Let's go look at this problem. Let me bring in this problem again. So by formal charge, we figure out this is what it's going to look like. But the double bond can actually be on the other side, right? Like, we could actually have, like, equally as acceptable, even with the formal charge, you could do it like this. Right? So the fact that these are two equally valid possibilities, this is resonance. So we call these resonance structures. And the way we show it is we show kind of like a double-headed arrow saying like, oh, it works between these two. So this is what resonance is. Now, actually what it is it's somewhere in between. So it's not like the double bond is fully here, and it's not like the double bond is fully here. It's kind of in between. It's almost like if you could have 1.5 bonds, like this is you can't do this, but I'm just showing it to you. If this was like 1.5, like I don't know how, maybe 1 electron, and this is 1.5. Like if you could do this, if this even makes sense, it's like that's what we're trying to show. It's like somewhere in between. So it's not like a full double bond and a full single bond. It's like a 1.5. It's like they're being shared. Because what's happening is these electrons are actually kind of floating throughout the molecule. They're not staying on in one place. And so it's kind of, but we don't have half bonds, and so we just say, hey, it's somewhere. It looks something in between these two. So it's something like that is what resonance is. Let's do some problems and kind of go from there, okay? So SO3 negative 2. So SO3 negative 2, 6, this is 6 as well, times 3, and then plus a 2, because it's a 2 charge, right? So this would be, let's see, what is 6, 18, 24, 26, right? 26 electrons. All right, let's go and do this. Sulfur, oxygen, here we go. So I used up 6, right? Here's 20. So if we do this right, it should look like this. Now what we got to do is check the formal charges. I'll do that in red. So let's look at this oxygen. This oxygen is let's see, this is 6 minus, there's 6 valence and 1. So this is the number of valence electrons in oxygen, minus 6, or 6 electrons, lone electrons, and then 1 bond. So this is negative 1. This will make this negative 1. This will make this negative 1. Okay? The sulfur, though, sulfur is, this is going to be, sulfur is 6 as well, minus 2, minus 3. This will give it a plus 1. So not great. We don't like this plus 1 charge here. All right, so what we can do is we're going to have to change this, kind of like we did before, and move this over here like this. Oops, sorry, I used a different color. This would be better because what it would do is it would now make this 6 minus 2 minus 4 would give me 0. This would now be, those would still be negative 1s, right? And then this would be 6 minus 4 minus 2. So this would also be 0. All right, so those would be my formal charges. So this is what it would look like And then what I would have to do is I would have to show resonance, because this double bond could be in any of these three locations. So let me just clear up the board here, and then I'm just going to draw my other possibilities. So a couple things. This is a -2 charge, right? So it would look like this, -2, and then I have to show resonance. I'm running out of space, so I'm just going to do it like this. So that's one possibility, -2, and then here's another one. I'm just going to try to squeeze it in here. So they could go this way, right? -2. So you can see those double headed arrows would also work here. Would show, that's what it's showing resonance. Like there's three possible structures. Okay. Let me do one more. Let's just do, yeah, let's do one more. I'm going to be running out of time. So sulfate is SO4, -2, so that's sulfate. So this would be 6, and this would be 24 plus 2. So this would give me 32. All right, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 20. So this is actually 32 right here, right? And the whole thing is -2. Hey, let's check this sulfur. So this sulfur, we're going to have problems here, huh? Because this sulfur is actually a 6 minus 0. It has nothing. Minus a -4 here. So this would be a negative or +2, which we don't like. So what we're going to have to do is we're going to need to get to the 0. We're going to have to put a couple bonds here like this. And so and it's possible because sulfur is in period 3. And so this is a little happier because now this is 6. And then, you know, there's a bunch of resonance, right? Like the double bonds can go into different places. So you would have to show the resonance here, right? Like, so you could have this, okay? You could have, and of course I'm not changing the electrons, but they would have to change. You could have that, right? You could have this. So there's a lot of possibilities that could occur. A lot of resonance structures for this particular one. All right. Let's do this one. This will be our last one for, so, and then the other ones, if you want to work on them and then show me, we can talk about that. Here's carbonate. So CO3 minus 2. So carbon is a 4, right? This is 18 plus 2. So this would be 24 electrons. So let's build it. All right, so this is 6 off 18. All right, and then that carbon needs an extra 1, so this one's going to be a little easier, I think. So if we look at this carbon here, oh, don't forget -2. So if we look at this carbon, let's do the formal charge. So it's 4 minus, no, there's nothing on, no lone pairs or lone electrons, but there are 4 bonds. So this is 0. Oh, that's good. So there's nothing we have to do to change this. The formal charge is 0. I think we're fine here. And so, but there is resonance, right? Like you could have carbon double bonded this way. like this, you could also have, let me do it over here. It could also be carbon double bonded down below there. Okay, so it could look like that as well. All right. All right, hopefully that helps. So once you get the structure you like, always check the formal charge, specifically on the central atom. If it's a 0, you're good to go. You also want to see if there's any resonance. If it's not going to happen, like if it maybe a +1 charge or a -1 charge, then you're going to have to kind of change things around so that you can get to a 0. Okay?